Okay, so today we will now discuss the emitter bias configuration. So this is your emitter bias. Now in this configuration, this is similar to the fixed bias circuit, but only difference is that we are connecting emitter resistance at the emitter terminal. So we will try to calculate the Q point from the circuit. Now the Q point in the circuit is always similar like ICQ. We will try to calculate the ICQ and the VCQ and try to see how the different parameter if changes the Q point will be fixed in this case, and what is the advantages of being used the emitter resistance here. Okay, so first look into the circuit. So I'm just first drawing the circuit. Okay, so this is your circuit, a very simple circuit, always similar to the fixed bias circuit, but the only difference is that there is a emitter resistance comes into picture. So if you just write the equation in the input loop, so this is your current IB and this is your current IC, this is your current IE, there is a voltage drop VB, there is a voltage drop VC. So we are just going to apply the 2 KVL at the output loop also and the input loop. From the input loop we will try to calculate the IB, and from there we will try to calculate the IC, and in the output loop we will try to calculate the VC. That is the main aim of our to calculate ICQ and the VCQ. Okay, so the input loop, if we just apply the KVL like this in this way, so your KVL will be VCC minus IBRB. So VCC, your VCC this is minus IBRB, next VBE, next IERE. So next your VBE minus IERE. This will be equal to 0. Okay, this will be equal to 0 volt. And also from the expression of the original transistor action, that IE is nothing but your IE will be nothing but IC plus IB, and your IC will be beta IB. So IC will be your beta IB, so this will be your IB. So your IE will be nothing but beta plus 1 IB. Okay, so this is the expression for IE equal to beta plus 1 IB, and I am just replacing it in this equation. So I am just removing this here. So if you just replace IE equal to beta plus 1 IB, then VCC minus IBRB minus VB minus beta plus 1 IB into RB is equal to 0. Now from there we will try to calculate the IB. So the expression for IB comes out to be VCC minus VBE VCC minus VBE divided by RB plus beta plus 1 RB. So this is one expression for IB. This will be also required for the understanding of how advantageous your RE is. Okay, so there is also another expression from there if we write down the expression for IB, or okay, we'll see it later, that how this value of IB will be taken care of. So I'm just also writing this from this equation. If we just write the value of 1 minute, this is the another expression for IB. Okay, so here I am just, this is the equation. So from that equation, if I am writing the value of IB from that equation, then it will be IB is nothing but this VCC minus VBE. So VCC minus VBE minus IERE. This expression will be required some point of time, RB. Okay, so this is the value of your IB, this is the value of your IB, this is the, there is a, this expression is there, and this is also, this expression is there, this is the two expression. Okay, so next from there we will try to calculate, if we want to calculate the IC. So IC equal to nothing but beta IB. So your IC will be nothing but beta, and what is the value of IB? VCC minus VBE, VCC minus VBE divided by RB plus beta plus 1 RB, RB plus beta plus 1, it is not RB, it is RE. Okay, so beta plus 1 RE. So this is the expression for IC. So we get the expression for IC. Okay, we get the expression for IC, that is the required for the Q point calculation. This is another point IC. Okay, so next we will apply the KVL at the output loop like this, KVL at the output loop. So if we just apply the KVL at the output loop, then what happens? VCC, just apply the KVL. So VCC minus ICRC minus VCE. Okay, so VCC minus ICRC minus VCE minus IE into RE, okay, equal to 0. So I am just writing the equation in the output loop. In the output loop, what happens? VCC minus IC into RC minus VCE minus IE into RE equal to 0. So this is the output loop expression. Now from that expression, okay, from that expression we know that the your IE in the transistor circuit, your IE will be approximately equal to IC. Okay, so from there, if you just replace this IE with your IC, then you will get the value VC, value of VC. I am just writing the value of VC here. VC equal to VCC minus RC plus RE, RC plus RE into IC. Okay, so this is the another voltage, okay, that will be required for the calculation of the Q point. So through Q point value will be get IC and VC. So in the load line we will just get the Q point, just IC and the VC. So this is the IC and this is the VC that we require for every biasing configuration. We want to calculate these two value. Okay, now the advantage of using RE. So what is the advantage of using the RE? Next, the advantage of using RE is that, so I am just writing advantage of using RE. What is the advantage of using RE? The first advantage is that, suppose as the I am said in the biasing configuration that your IC will be fixed and the VC will be fixed. Now what happens if the temperature increases? The simple configuration, if the temperature increases, what happens? Your IC will increase. Now if the temperature increases, why IC will increase? Because in the expression for the IC you will encounter that IC expression is beta IB plus beta plus 1 IC naught. Now this IC naught is responsible because IC naught is nothing but the reverse saturation current at the collector junction. So what happens if the temperature increases, this reverse saturation current will also increase, that is also increasing the value of IC. Now if the IC will change, then the operating point will also change. Now how the emitter resistance will compensate that? Now we know IE is nearly equal to IC. Now this IE-RE, okay, can be approximated at IC-RC. So you can approximate that IE-RE is nearly equal to IE-RE is nearly equal to IC-RC, because transistor IC equal to IE, almost equal to, okay, if beta is very large. So the drop, if IC increases, this drop across this IC-RE, IC increases, so this is the voltage drop across the emitter, so this drop will also increases, this drop will also increases. So this you can say that the IE-RE drop, the emitter resistance drop, will also increases. Now if this emitter IE-RE is also increases, I am just writing this equation for the IB. So you can see, if this IE-RE is increases, then what happens, this IB value will be decreases, because this is a difference term, okay. So if IE-RE will be increases, IE-RE, if this IE-RE drop will be increases, that what happens, your IB will be decreases. Now also the expression for IC, you can say beta IB, okay. Now is IB will be decreases, so your IC will be also decreases. So the temperature which will try to increase the temperature which will try to increase the collector current, then what happens, the emitter resistance comes into picture, and the drop across the emitter resistance is increases, and as the drop is emitter resistance is increases, so base current is also start reduce. As the base current is try to reduce, so this collector current will starts to reduce. So that's why this emitter resistance will help us to stabilize the circuit, okay. So next advantage is that if the beta is changes, that means if the beta value is higher, okay, so what happens, we want to make the transistor current independent of beta. So because IC will actually be dependent on beta IB, so the expression I have written down here, I'm just copying the expression, this expression, so 1 minute, this expression, okay, so this expression, so this will be your expression for IC. Now IC equal to beta. Now if beta increases, if your beta increases, then IC value will obviously increases, because IC equal to beta IB, this is the expression for IB. Now you can see from that expression that this beta plus 1 RE, if we make this value very much higher than this value, very much higher than this value, then what happens, this value is very much higher than this value, then you can ignore this value. So if you just can ignore this value, so what happens, beta VCC minus VBE divided by, and beta, if this value is very higher, so actually beta is very higher, so beta plus 1 RE is approximated at beta RE, okay. So you can cancel beta, so IC will be totally independent of beta, okay. So IC will be totally independent of beta, independent of beta, okay. So that is the another requirement for how the this emitter resistance will help us to make the collector current fixed, okay. Collector current fixed in also temperature neutral and also beta neutral, this is the both the case. But one disadvantages of is that if we want to make that means beta is unknown to us, beta is actually unknown to us, if then we want to try to make this RE is very much higher, RE is very much higher, and RB is very much lower, okay. So that is the main disadvantage, that we want to make the RE very much higher, so that is not feasible actually in the circuit or the practical point of view, okay. So that is the one small disadvantage that you will not consider. But here the IC will try to independent with respect to temperature and with respect to beta, that is our main advantage of using the emitter resistance at the emitter terminal at the fixed bias circuit. Okay.